Hello students, welcome to the class Mathematics. In this class, we are going to discuss the basic terms and important concepts in the chapter sets. Generally, we give a lot of importance to the group of students, group of teachers, group of workers, that is students union, teachers union, workers union, etc. These groups are formed on some purpose. In the same way, in mathematics also, when you solve any problem, in the most of the cases, we give the solution in the form of collection of numbers. For example, collection of all the real numbers is the solution, or collection of all the numbers of the form n square plus 1 is the solution, etc. So, it is very important for us to learn about collection of objects and well-defined collection of objects. For that, let us consider one collection of objects, that is collection of all the good books in your school library. Now, for this collection, showing one book to you, I am asking you whether this book belongs to this collection of all the good books in your library or not. Can you decide? Actually, you can't exactly decide, because if you feel that this is the good book, you will say that this book belongs to that collection or this collection. If I ask another student, that student may not like this book, of course may not feel that this is the good book, then automatically that student, another student may say that this book does not belong to this collection of all the good books in your school library. So here, from all the students, from all the persons, can you get the same answer? So we can't get the same answer. It means we can't exactly decide whether this book belongs to this collection of all the good books or not. So it is just a group. Now let us take another collection of objects, that is collection of all the multiples of 5 less than 100. Now let us take the number 6. Now can you decide whether this number 6 belongs to this collection of all the multiples of 5 less than 100 or not? We can easily decide. As 6 is not the multiple of 5, we can say that 6 does not belong to this collection of all the multiples of 5 less than 100. So in this case, whatever number is given to you, you can easily decide whether that number belongs to this collection or not. So such a collection of objects is called a well-defined collection of objects. But in the previous case, for that collection, we can't decide whether the given object belongs to that collection or not. It is just a group. But here in this case, we can decide whether the given object belongs to this collection or not. Such a collection of objects is called a well-defined collection of objects. So, children, such a well-defined collection of objects is defined as the set. So finally, students, we can define the set as a well-defined collection of objects. Generally, sets are denoted by the capital letters like A, B, C and so on, and the elements or objects in the set are denoted by lowercase letters like X, Y, Z and so on. Generally, we describe the sets mainly in two different forms, that is list form, also called roster form. The second one, rule form, also called set builder form. Now, taking one set, let us see how to describe that set in these two forms. For that, let us take collection of all the perfect square numbers less than 50. Now, first let us decide whether this collection is a well-defined collection or not. For that, first let us take one number 10. Now, can you say that the number 10 belongs to this collection? We can clearly say that the number 10 does not belong to this collection because 10 is not a perfect square number. So, 10 does not belong to this collection of objects. Next, let us take another number 36. Now, can you decide whether 36 belongs to this collection of all the perfect square numbers less than 50? We can easily decide because 36 is the perfect square number and also less than 50. So, we can say that 36 belongs to this collection. Now, we can say that this collection of all the perfect square numbers less than 50 is a set. It's because it's a well-defined collection. That's why it is a set. Now let us rewrite this collection as set of all the perfect square numbers less than 50. Now let us try to describe this set in the first list form. To describe this set in the list form, first of all, we have to list out all the elements which belong to this set. So what are the elements which belong to this set? All the perfect square numbers less than 50. What are the perfect square numbers? 1, 4, 9, 16, 25, 36, 49. First we have to list out all these perfect square numbers less than 50. Now we have to put all these numbers in the braces like this. Now this form of description of set is called list form or roster form. Now let us describe this set in the set below form, that is rule form. To describe the set in the set below form, first we use the property which is common to all the elements in the given set. What is the property which is common to all the elements in the given set? If you observe, all the elements are the perfect square numbers less than 50. That is 1 square, 2 square, 3 square, 4 square, 5 square, 6 square and 7 square. So all are perfect square numbers. So with the help of this common property, we will describe the set in the set below form. First we use the notation x square to represent the perfect square number. So here we have to describe the variable x. Now what can you say about the x, variable x? Here x is taking the values from 1 to 7, that is 1, 2, 3, 4, 5, 6, 7. So as x is taking the values 1, 2, 3, 4, 5, 6, 7, we can say that x is a natural number. So x belongs to n. And also x is taking the value up to 7. So x is less than or equal to 7 or x is less than 8. Now if you write all these conditions in the set form, that is set of x square, such that x belongs to n and x is less than or equal to 7. This form of description of a set is called a set below form.
Students, let us consider the set A is equal to set of 2, 4, 6, 8, 10. Here we can see that the element 2 is a member of the set A. So we write this relation as 2 belongs to A. Suppose you consider any number like such as 9. 9 is not a member of this set A. So we write 9 does not belong to A. And also the number of elements in the given set A is called the cardinal number of the given set A, that is denoted by n of A. So here in this given set, how many elements are there? There are totally 5 elements. So here for the set A we write n of A, that is a cardinal number of A is equal to 5.
Now let us discuss the types of sets. First one is finite set. A set with a limited number of objects is defined as a finite set. For example, A is equal to set of 2, 4, 6, 8, 10. Here, in this set, there is a limited number of elements. That is, here, in this case, we can count the number of elements in this set A. How many elements are there? There are totally 5 elements. As we are able to count the number of elements in this set is taken as an example of a finite set. Next one, infinite set. A set with an unlimited number of elements in it is defined as an infinite set. For example, B is equal to set of all the even natural numbers. If you write this set in the list form, you will get B is equal to set of 2, 4, 6, 8, 10 and so on. Now in this case, how many elements are there in this set? Can you tell? We can't tell the number of elements in this because there is an unlimited number of elements in this set B. So we can't count the number of elements. So this is an example of an infinite set. Next one, empty set. A set with no elements in it is defined as an empty set. An empty set is also called a void set or a null set, and it is denoted by the symbol phi or empty braces like this. The example for an empty set, let us see now. A is equal to set of all the natural numbers less than 1. Can you find any natural number less than 1? We can't find any natural number less than 1. So A is equal to set of no elements. So it is an example of an empty set. Let us take another example. B is equal to set of x such that x belongs to R and x square is less than 0. Here, can you find any element in this set? Here also we can't find because there is no real number whose square is less than 0. We know that the square of any real number is always non-negative number. That's why the square of a real number can never be less than 0. So the set B is also an example of an empty set. Next set is a singleton set. A set with only one element in it is defined as a singleton set. For example, A is equal to set of all even prime numbers. Now tell me students, how many numbers are there which is both prime and even? There is only one number, that is 2. So A can be taken as a set of 2. As this set A has only one element 2, this set is taken as an example of a singleton set. Now let us discuss some important relations between the sets. First one is subset. The term subset is very important relation between the sets in the set theory. For this, let us consider two sets. And if you can observe that if each and every element of the first set is an element of the second set, we can say that first set is a subset of second set. Now let us try to understand this concept through one example. For this, let us take two sets A and B.
A is equal to set of 1, 3, 5.
And B has some elements in it. And we have observed that the element 1 of A belongs to set B. the element 3 of A belongs to second set B, and also the third element 5 of A belongs to second set B. Here, each and every element of A is an element of B. Now, can you say that the sets A and B are equal sets? We can't say, because here we can see two possibilities. In the first possibility, B has exactly the same elements what A has. That is, B is equal to set of 1, 3, 5. In this possibility, A and B are equal sets. In the second possibility, B may have some extra elements, at least one extra element, which is not in A. So in this case, we can't say that A and B are equal sets. So whatever possibility they may have, in this case, what is that case? If each and every element of A is an element of the second set B, we can say that the first set A is a subset of second set B. Now, the relation A is subset of B is denoted by the notation A is subset of B, like this. In this case, A is subset of B, the set B is called superset of A. It is denoted by B is superset of A, like this. The next term is proper subset. If the set A is a subset of set B and A is not equal to B, then A is said to be a proper subset of B. It means if the set A is a subset of the set B and A is not equal to B, which means B has some extra elements or at least one extra element which is not in A, then we can say that the set A is a proper subset of set B. This relation A is proper subset of B is denoted by A is a subset of B without equality sign below the subset symbol.
Let us make some observations on subsets. First one, every set is a subset of itself. For this, let us take two sets. A is equal to set of 1, 2, 3 and B is equal to set of 1, 2, 3. Here clearly we can observe that A and B are equal sets. Now, every element of A is an element of B. So, here we can say that by the definition of a subset, A is subset of B. And also these two sets are equal sets. Finally, we can say that every set is a subset of itself. That is, A is subset of A and set B is a subset of B and set P is a subset of P. Second one is null set is a subset of every set. If A is any set, we can say that phi is a subset of A. Actually, to prove that one set is not a subset of another set, it is enough for us to show that if an element which belongs to first set does not belong to second set, we can say that first set is not a subset of second set. But here we can't find any element in the null set which does not belong to second set. So we can't say that null set is not a subset of set A. So finally we can conclude that null set is a subset of every set. That is, phi is a subset of A. If the set A has n elements in it, then the number of subsets of A is 2 power n. The number of proper subsets of A is 2 power n minus 1. And also the number of non-empty proper subsets of A is 2 power n minus 2.
The next term is equal sets. Two sets A and B are equal sets if they have the same elements. It means each and every element of the set A is an element of B and each and every element of the set B is an element of the set A. That is, A is subset of B and B is subset of A. In this case, both the sets A and B have the same elements. So, they are called equal sets. The equality of two sets A and B is denoted by A is equal to B like this. The next term is equivalent sets. Two sets A and B are equivalent sets if they have the same number of elements. For example, A is equal to set of 1, 2, 3, 4, 5 and B is equal to set of A, B, C, D, E. Here, the sets A and B have the same number of elements. That is, A has 5 elements and also B has 5 elements. So, as their cardinal numbers are equal, that is, n of A is equal to 5 and n of B is equal to 5. As they are equal, we can say that these two sets A and B are equivalent sets. If A is equivalent to B, that relation is denoted by like this. Now let us define another term, disjoint sets. Two sets A and B are disjoint sets if they have no common elements. For example, A is equal to set of 1, 2, 3 and B is equal to set of 4, 5, 6. Here, the sets A and B have no elements in common. So, these type of sets are called disjoint sets. If the sets A and B have at least one element in common, then they are called joint sets. Now let us define another term, a universal set. Let us try to understand the universal set through one example. You see, children, every year school or college conducts games and sports for the children. For that, it selects some teams such as cricket team, hockey team, kabaddi team, kho-kho team, etc. Here, we can observe that the students in each and every team are taken from the students in the school. And in this case, if you treat all these teams of students and the students in the school as sets, we can observe that all these sets are subsets of set of students in the school. And so, the set of all the students in the school is taken as a superset in this case. This superset is defined as a universal set. So children, from this discussion, we can finally say that the set for which all the sets under consideration are subsets is defined as a universal set. The universal set is denoted by the symbol mu like this.
Students, let us study the sets through the diagrams which are called Venn diagrams. These diagrams are introduced by the mathematicians Euler and Venn. That's why these diagrams are called Euler-Venn diagrams, simply called Venn diagrams. These Venn diagrams are more effective for us to understand the operations between the sets. Generally, we use simple closed figures to represent the sets, but for our convenience, we mostly use rectangle and circles to represent the sets. First, let us describe the sets A and B when they are disjoint sets. As we know that all the sets under consideration are subsets of a universal set, first of all, we draw the rectangle to represent a universal set. And we know that A and B are disjoint sets. As they have no any common elements, we draw the circles to represent A and B separately. If the sets A and B are joint sets, we draw the circles for A and B like this. If the set A is a proper subset of set B, we draw the circle representing the set A completely inside the circle representing the set B like this.
Now let us discuss some important operations between the sets. Of all these, the first one is union of two sets. The union of two sets A and B is defined as the set of all the elements which belong to A or B or both. The union of two sets A and B is denoted by A union B like this. Now let us take one example. A is equal to set of 1, 2, 3, 4, 5 and B is equal to set of 4, 5, 6. Now their union, that is A union B, is defined as set of 1, 2, 3, 4, 5, 6. Here we observe that the elements 1, 2, 3 belong to the set A. The elements 4 and 5 belong to both the sets A and B, and the element 6 belongs to only the set B. So from this we can describe the set A union B in the set builder form as set of X such that X belongs to A or X belongs to B or X belongs to both. Here we need not mention X belongs to both because we are using the term or in inclusive sense in mathematics. What does it mean? Whenever you say X belongs to A or X belongs to B,
there may be a chance for them to be in both the sets.
So it is enough to write to describe the set A union B as set of X such that X belongs to A or X belongs to B. But generally, other than mathematics, we use the term or in the exclusive sense in our daily life. For example, you want to join some college for the completion of some course. For that, you have only two options, college A or college B. Then what do you say? I have to join either college A or college B. It means you will join in any one of the colleges. It does not mean that you will join both the colleges at a time. So here we are using the term or in the exclusive sense. So that is the difference between inclusive sense and exclusive sense of the term or. Now let us try to understand the set A union B through the Venn diagram. For this, first let us take one rectangle to represent a universal set and two circles to represent the sets A and B. Now let us shade the region of A with the horizontal lines and the region of B with the vertical lines. Now here the region with the horizontal lines will represent only the set A and the region with the vertical lines represents only the set B, and the region with the mesh portion will represent common portion of A and B. Now the entire shaded region will represent the set A union B. The next operation is intersection of two sets. The intersection of two sets A and B is defined as the set of all the elements which belong to both the sets A and B. The intersection of two sets A and B is denoted by A intersection B like this. Now let us take one example. A is equal to set of 1, 2, 3, 4, 5 and B is equal to set of 4, 5, 6, 7. Now the set, the operation A intersection B is taken as the set of 4, 5. Here, if you observe the elements in the set A intersection B, the elements 4 and 5 belong to both the sets A and B. So, we can describe the set A intersection B in the set builder form as set of X such that X belongs to A and X belongs to B.
Now let us see the Venn diagram of the set A intersection B. By the definition, the set of all the elements common to both the sets A and B is defined as intersection of the sets. So, let us shade the region which is common to both A and B. So, here we can see the common region for both the sets A and B. Now I am shading. This shaded region will represent the set A intersection B.